All right, this is a continuation of graphing rational functions. We're going to find all the important pieces. So in a previous lesson, we found the zeros or x-intercepts of a rational function by setting the numerator equal to 0 and solving for x. We also found vertical asymptotes by setting the denominator equal to 0 and solving for x. What's new is now finding the holes in the graph. They occur when you have a 0 in the numerator and the denominator. So you have a 0 in both the numerator and the denominator. So what we have is a 0 at that common factor of x plus 1. So what we do is we set the common factor equal to 0 and then solve for x. So we have a 0 at x equals -1. In some cases, both the numerator of the rational function will equal 0. As a result, the function will become undefined at this x value. If this is the case, the graph of the function may have a hole, and then the hole is omitted in this point. If the rational function has the same factor, and that's what this one was, it has the same factor in both the numerator and denominator, then there is a hole in the graph at that point where x equals b, and that is considered a vertical asymptote. Part D, horizontal asymptotes. To find the horizontal asymptote, we have to look at the value of which the y approaches the absolute value of x. So there's going to be 3 scenarios. If the degree of the numerator is equal to the denominator, then you will have to divide the leading coefficient. So here's an example. The degree in the numerator is 2. The degree in the denominator is 2. They're the same. So what you do then is you divide their leading coefficients. You take 6 over 2, which reduces to 3. So you'll have a horizontal asymptote at y equals 3. If the degree of the numerator is less than the degree of the denominator, then you'll have an asymptote at y equals 0. So the degree of the numerator is 2, and then the denominator is 3. So the numerator is smaller than the denominator, so you have it at y equals 0. The last scenario is if the degree of the numerator is greater than the denominator, then you will not have a horizontal asymptote. And we'll learn later about slant asymptotes. The last thing is to find the y-intercept. What we do is we evaluate the function for f of 0. So here's an example. We have a rational function, and we're going to start by finding the x-intercepts. So we focus on the numerator. We set the numerator equal to 0 and we solve for x. We're going to factor this. So we can go ahead and do our diamond. So we say, what are the factors of -4 that add to -3? And that's -4 and +1. And then we set those factors equal to 0 and solve for x. So we get an x equals 4 and x equals -1. So the order pairs would be -1, 0, and +4, 0. So here's an x-intercept and an x-intercept. Then we find the vertical asymptote. So that's the denominator, and it's the 0 in the denominator, so we set x equals 0. So here is our vertical asymptote at x equals 0. Then we want to find the horizontal asymptote. So the function, I'm just focusing on the first term and the first term. So I have an x squared divided by x to the first. Now, the degree of the numerator is 2, and the degree of the denominator is 1. So if we go back up to our rules here, the degree of the numerator is greater than its denominator, so we will not have a horizontal asymptote. So this is a none. To find our y-intercept, we evaluate the function for f of 0. And we get -4 divided by 0, which this makes this undefined. So we do not have a y-intercept. All right, example 2. We start by finding the x-intercept. We set the numerator equal to 0, and we solve for x. So we can add 12 to both sides, and then divide both sides by 4. So we get x is 3. So our x-intercept is at the ordered pair 3, 0. The vertical asymptote is the 0 of the denominator. Solve for x. So here's our vertical asymptote at x equals 1. Horizontal asymptote, we look at the degree of the numerator and denominator. So 4x to the first, x to the first. Both the degree of the numerator and the denominator are 1. They are the same. So if we go up to our rules, when they are equal, right here, you take the coefficients and you divide them. So we're going to take 4 divided by 1. So 4 divided by 1 is 4. So we have a horizontal asymptote at y equals 4. Last is to find the y-intercepts. We evaluate the function for 0. And then we simplify 0 minus 12, 0 minus 1, -12 divided by -1 is positive 12. So we have a y-intercept of 0, 12, so up here. All right, here's another one. We want to find the holes in the graph, so we start with the numerator. We solve it for x. So this one we can solve by undoing. Actually, we need to factor this first to see if we have any holes in the graph. So I'm going to factor the numerator as the difference of 2 squared, so x plus 3, x minus 3, and the denominator just stays as x minus 3. All right, so what we have is a common factor of x minus 3. So that's going to produce a hole in the graph. So if we go back up here, our holes in the graph are when we have a common factor. So we set that common factor, x minus 3, equal to 0, and then solve for x. So here is 3, and we go up, there is going to be that hole in the graph. How we find that hole in the graph is we evaluate the function. So what's left after we cancel the holes in the graph, we're left with f of x equals x plus 3, a nice linear function. And then we evaluate the function for f of 3. So 3 plus 3 is 6. So this hole is at over 3 up 6. Our vertical asymptote, the denominator, we set that equal to 0 and solve for x. And that's where that hole is. Then what's left when that function was x plus 3. So we have a linear function that looks like this. It has a slope of 1 and a y-intercept of 3. So we do not have a horizontal asymptote. Our y-intercept is right here at 0, 3. You can evaluate the function for 0. And you get 0, 3.